So we talked about algorithms. Now let's talk about what makes a good algorithm. So ideally, we'd like an algorithm that's correct. We'd like an algorithm that produces correct input for all valid outputs, or correct output for all valid inputs. This is not necessarily something that's required. We have plenty of algorithms that are approximate that don't produce correct inputs, but in general, we want something that's correct. We want something that's efficient, uses minimal resources in terms of time and memory. We want something that's scalable, handles large inputs without a sharp increase in resource usage. We want clarity and simplicity, easy to understand, implement, and debug. We want robust. We want it to handle edge cases and incorrect input gracefully. We want something that can be reused and extended with minimal changes. So time complexity measures how runtime grows with input size n. So common classes O1, O of log n, O of n, O of n log n. I'll show you how these compare in the next slide. Space complexity measures how memory usage grows with input size. Best case scenario is how quickly the algorithm runs in perfect conditions. This can be useful because sometimes you want an algorithm that works really well most of the time. Average case, average case is the expected over all inputs. Also very useful because sometimes you don't really care much about the worst case. And worst case is what we normally think of in terms of time complexity, which is how well the algorithm runs in the worst possible conditions. Because when we think about algorithms, we're thinking about how we're thinking about something that we want to solve everything. We want to solve even the bad cases pretty quickly. So asymptotic analysis focuses on the behavior as input size grows to infinity and ignores constant factors in lower order terms. So here's how you can sort of think of asymptotic analysis. The worst possible computational complexity is O of n squared, or O of n factorial, or so it grows very quickly. Then you have exponential 2 to the n, e to the n. Then you have all these polynomial examples. Then you have quadratic n squared, a lot better than exponential, but still not great. Then you have log linear, n log n. Then you have linear. Then you have logarithmic, which grows slower than the inputs. And then you have constant, where you only have to do one operation. Standardizing algorithms from pseudocode, function find max. Max equals a of 0 for I equals 1 to length of a minus 1. If a of I is greater than max, max equals a of I. So you're just comparing between each of the two. This line runs in constant time. This loop runs n minus 1 times. Each iteration in comparison for assignment runs in constant time, and then return max runs in constant time. So this is O of n because you have a loop that runs n minus 1 times, which as n goes to infinity goes to n. So here's quadratic times where we have nested for loops. So this is an O of n. Here's another O of n. So we have a has pair with sum. So you're checking whether or not there is in the list a pair of two numbers that sum to target, and you're returning true if it does. In the worst case scenario, this is going to run n minus 1 times. This is going to run n minus 1 times. This is going to run n times. It's going to run up to n minus I minus 1 times. And so the total iterations is n minus 1. N minus I minus 1 equals n squared. So n times n minus 1. So I minus 1, which asymptotically is n squared. So each comparison inside the inner loop is O of 1. So this grows quadratically. Merge sort versus double sort. This is to show you that even if two algorithms have different time complexities, they might also have different space complexities. So merge sort is the best in terms of all features, in terms of the average case, in terms of the worst case, for time. Bubble sort's a little bit better if it's already sorted, but otherwise, merge sort is significantly better. But in terms of space, bubble sort takes only one, whereas merge sort takes O of n, and this is because bubble sort only stores the initial list. So this is something I want you to be aware of that's very common in machine learning, is you have this idea of a time-space trade-off, where if you have an algorithm that takes up more time, often it will also take up less space, and the opposite in the other direction. So here's Fibonacci sequence without dynamic programming. So we have the naive recursive definition, which is f of n equals f of n minus 1 plus f of n minus 2. So we're just going to do function fib of n is if n equals 1, return n. If n is less than 1, rather, return n. And return fib of n minus 1 plus fib of n minus 2. Time complexity is 2 to the n because you're calling it a lot. You also have to remember a lot. So here's kind of what that tree looks like right there. And then with dynamic programming, we initialize a table, and then we call the table with the smaller numbers, and we build up. So now we don't have to compute each computation over and over again. We don't need redundant computation. We solve the subproblem exactly once. So computational complexity is very important in machine learning because machine learning often deals with large data sets, and we care a lot about scalability. Faster algorithms allow more iterations, hyperparameter tuning, and real-world learning. Efficient algorithms minimize RAM and GPU usage, which is very essential for deep learning, which requires massive data sets and can grow in terms of RAM very quickly. And model deployment inference must be fast and lightweight, especially for mobile or edge devices. Thank you, and that was our look at computational